Hello everyone. Today we will understand how to calculate the electric field intensity due to uniformly charged spherical cell. To find it, we are going to apply Gauss Law. First we consider that charge capital Q is distributed uniformly over the surface of a spherical cell of radius capital R as shown in the figure. Electric field lines due to this charge distribution is radially outward. If we have to find electric field intensity at outside point at the distance small r from the center of the cell, then we consider a spherical Gaussian surface of radius small r concentric with the cell. As we have discussed that electric field intensity at the Gaussian surface is radially outward. If we consider an elemental area at the Gaussian surface, then electric field intensity will be perpendicular to it. Now we can say that electric field intensity and area vector both are radially outward. Now we can write the elemental area vector and electric field according as now we find electric flux through the Gaussian surface by using the formula phi equal to closed integration vector E dot dA. On putting the values of vector E and vector dA, we get, on solving it, we get phi equal to closed integration E into dA. Gaussian surface is symmetrical about the charge distribution. Therefore, the magnitude of electric field intensity at every point at the Gaussian surface is constant in magnitude. Therefore, capital E comes out from the integration, and on solving we get the electric flux phi equal to E into 4 pi small r square. Since a spherical cell is completely inside the Gaussian surface, therefore total charge enclosed inside the Gaussian surface must be equal to the charge to the cell. Therefore, Q enclosed equal to capital Q, which is the charge to the spherical cell. Finally, we apply Gauss law. Phi equal to closed integration vector E dot dA equal to Q enclosed upon epsilon naught. On putting the values of electric flux and charge enclosed inside the Gaussian surface. On solving, finally we get E equal to 1 upon 4 pi epsilon naught Q upon small r square. To find electric field intensity at the surface of the cell, we draw a spherical Gaussian surface which just encloses the charged cell. In this case, the radius of the Gaussian surface just become equal to the radius of the charged cell. As discussed in previous section that electric field intensity at the Gaussian surface is radially outward. Therefore, if we consider an elemental area at the Gaussian surface, then electric field intensity and area vector both will be radially outward as in previous section. Therefore, we use similar argument as in previous section to find the electric flux through the Gaussian surface. The magnitude of electric field intensity at the Gaussian surface is constant in magnitude due to symmetrical charge distribution. Therefore, capital E comes out from the integration. Finally, we get electric flux phi equal to capital E into 4 pi capital R square. Cell is completely inside the Gaussian surface, therefore charge enclosed within the Gaussian surface must be equal to the charge to the cell. Therefore, Q enclosed equal to capital Q. Now we apply Gauss law to find the electric field intensity at the surface of cell. Put the values of electric flux and Q enclosed. We get the electric field intensity at the surface of the cell. Capital E equal to 1 upon 4 pi epsilon naught capital Q upon capital R square. To find electric field intensity inside the cell, we draw a spherical Gaussian surface having radius small r smaller than the radius of the cell, as shown in the figure. In this case, the charge distributed over the surface of the cell is completely outside the spherical Gaussian surface. Charge enclosed inside the Gaussian surface, Q enclosed, is 0. Since charge enclosed inside the Gaussian surface is 0, therefore, according to Gauss law, total outward flux through the Gaussian surface must be 0. Therefore, we get closed integration vector E dot vector dA equal to 0. It gives electric field intensity inside the cell capital E equal to 0.